Welcome back, Quadrature fans. Today, geometry for quadrature, Cavalieri shift, take 3. Last time we left at, well, basically under a Cavalieri shift the area remains invariant. And we also said that the slope remains invariant. So, interesting. So you do this. And so the ratio of areas is also constant, and the ratio of slopes is also constant. So what does that look like in terms of the algebra? Well, I got an application here that basically we have our y equals x squared. You've seen this before, right? So we're going to apply y equals x squared and figure out how the slope works, how the area works. And we've done this before, so it'll be kind of a review. But look at this. We're using Wahlberger's additivity, linearity, translation, dilation, normalization. These are properties of areas, and they're kind of, this would be kind of the invariant. Think of this as the invariant. They're invariant properties of areas. Okay. So when we do translation, which is x equals a plus t, look at this. We got 0a, 2a on the x-axis. And then on the t-axis, it's minus a, 0a. That's translation. You plug that in to x squared, you get a plus t squared, which takes us to our Pascal triangle 1, 2, 1, so it's 1a squared plus 2at plus 1t squared. But it doesn't have to be a squared plus 2at plus t squared. It could be t squared plus 2at plus a squared. It could be 2at plus a squared plus t squared. It could be a squared plus 2a squared plus t squared. And there is no specified order that the binomial expansion tells us. It doesn't have to be this goes on the top or first, this is the second, this is the third. There is no order. It's all acting together. But there are 3 elements, so we have to list them. So I'm using this kind of linear algebra structure to kind of show the 3 elements, but there really is no implied order of these. This is the commutative property of algebra, right? You've heard of commutative. You can switch the order any way you want to, and you haven't changed the equation. Now look at the corollary, the geometric interpretation of, let's say, this. If we have t squared plus 2at plus a squared, well, at t equals a, here we got a squared. This is our quadratic. Here's our 2at, that's our linear. Notice at t equals a, it's 2a squared. And a squared, this is our constant. And then you can see the similar thing is here. There's our linear 2at, here's our constant, and here's our quadratic. Well, same thing here. Here's our constant, linear, and quadratic. And it's all the same thing. It's the same thing in terms of algebra. It's the same thing in terms of geometry. Well, that's what I'm saying, that my geometry can't really distinguish between this, this, and this, and they're all the same. Well, let's look at this. I mean, is this any different? Here's a squared, 2at t squared. You've seen this, right? Well, I can downshift it. I can downshift all these, and that's going to look like this. You see what I'm doing? We're doing Cavalieri type shifts. And so we get this shape. And so here's a squared. But I can also kind of shift it like this. And I can go further. I can make it look like this. And the geometry of this Cavalieri shift, this affine geometry, doesn't really distinguish this, or even this. Or even if you swap these, it can't tell any difference. It's totally oblivious to anything like that. It's oblivious from the area point of view, but it's also oblivious from the slope point of view. It can't tell. One way to look at it is kind of the bird's eye view from the top, projective geometry. So you look at this, the run is always 0 to A. You can't tell the difference if you're looking at it from space. Okay, interesting. So let's look at our slope equation. This is the thing that really got me thinking this, where the slope is invariant. Look, from the x perspective, the slope over here, well, that's rise divided by run, that's our characteristic diagonal, times C2, some invariant. C2, which let's say we don't know what C2 is. We estimated it to be 2. We will prove that it is 2. That's from the x perspective. Well, that equals, you can break that up into 3 components. You got your flat, 0. Here's your linear, that's 1 times, because it's the first order. It's 2a squared divided by a. And the quadratic, that's C2, a squared divided by a. All right, I think you've seen this in my previous videos. So essentially you got a squared over a squared over a squared over a. And that simply simplifies to C2 times 8 equals 2 plus C2. And of course, if you solve this, you get one equation, one unknown. You get C2 is equal to 2, exactly 2. We're saying that our invariant here, C2, is 2 for a quadratic. 2 times the characteristic diagonal, that gives you the slope over here, the tangent slope. Similar for area. But with area, of course, we're doing K2. From the x perspective, it's 4a squared times 2a. It's the rise times the run. Okay? Well, that equals these 4 areas right here. That's K2, and that's a squared times a. Plus, you got now your constant, linear, and again our quadratic. The constant is 1 times a squared times a, because it's on the t-axis. And then our linear, well, that's 1/2. That's a triangle. The k factor for triangle is 1/2 times, well, what is it? Well, it's 2a squared times a. That's this one here. And then finally is this shape here, and that's again K2 times a squared times a. And you might say, well, this doesn't look like this. Well, yes it does, because what we're going to do is we're going to do a Cavalieri shift right here. You see what we're doing? We're shifting it, right? We're just downshifting it. And area doesn't change. It's constant under this shift condition. And we're seeing that. Here's Cavalieri's principle illustrated. Here's the algebra of it. It's the same. You see it. It's the same. Absolutely the same. So, okay, cool. Here, the a squared times a, that cancels out. And did I make a mistake here? I sure did. This would be 2. C2 times 2. Sorry about that. This one is a K2 times 8. That equals K2 plus 1 plus 1 plus K2. Okay. So here we have one equation, one unknown. You solve it. K2 is 1/3. Very easy. That was a piece of cake. One more thing. Look at the relative slopes and relative areas of all these things. Well, the relative slopes, if you normalize, divide by C2, well, you would get 2 equals 1 plus 1. 1 plus 1. You see this? These are the relative weights of these slopes. Okay? So it's in a ratio of 1 to 1, or proportion of 1 to 1. What about the areas? You've got 4 areas, 1, 2, 3, 4. If we normalize by K2, we get 8 equals 1 plus 3 plus 3 plus 1. You simply divide everything by K2, which is 1/3, and this is the relative weights or relative areas. Normalized, basically this would be the smallest area, and you can see it's 1 to 3 to 3 to 1. Again, 1 to 3 to 3 to 1. You see these lovely ratios. And of course the function itself is 1 to 2 to 1. 1 to 1. So the binomial expansion, it's working beautifully here. It's working for the function itself. It's working for the slope. It's working for the area. In the slope, we lose a term because we're flat. That's 0. So we lose a term. Interesting. Okay. In the area, we gain in a term. It's this one here. It's the 4th area that pops up. Very interesting. So here we have 4 elements here. The original function is 3 elements. So beautiful stuff. Here we're making connection with a lot of things. Cavalieri's principle, this idea that, here we're just downshifting. Well, during Cavalieri's time, he didn't have much of a notion of a limiting process. He did use it, or call it method, no, not method of exhaustion, but indivisible. Basically, here you have a deck of cards, and if you make this card so small that it's indivisible, then it's going to be perfectly smooth. You get perfect continuous. So here we have Cavalieri principle makes contact with the notion of what we in modern times call a limit, or limiting process. And that makes contact with the notion of the nature of the continuum. As you go to indivisible, then there are less jaggies. Right now, if you look closely, you can actually see there are little discontinuities in here. As you go toward indivisible, you can't see that. There's no discontinuities, so-called. So this is so much going for it, But this equation right here, the slope equation, is kind of what got me thinking that this is true here as well as here. Okay, think about it. This equation wouldn't work otherwise. It works here. It's true for this case here. It's true. It's indistinguishable. It's one equation. Here we're seeing Cavalieri principle right here from an algebra perspective. It's the same area. This and this is the same. You cannot tell. It's indistinguishable. So we've got all these things going for us. This is the invariant. Added to the linearity, translation, dilation, normalization. Cool stuff. Anyways, so remember, before there was calculus,
there was quadrature.
You got it.